Good morning. Today's lecture is the last one in our kinetics, equilibrium, and thermodynamics unit. We are still focusing on thermodynamics, and we're trying to now finally look at the big picture. So what is it that makes chemical reactions happen? Well, earlier this unit, when we were studying kinetics, we learned that particles must collide with the proper orientation and sufficient amount of energy. That's called the collision theory. What we've started to learn recently is that they must also be thermodynamically favored. Thus far, in the thermodynamic portion of the unit, we've learned about enthalpy. What we have here are these three bullets that constitute the laws of thermodynamics. And there are three of them. The first law says, when energy passes into or out of a system, the system's internal energy changes so that the law of conservation of energy is followed. In other words, energy is neither created nor destroyed, it is simply transferred. The law of conservation of energy and the law of conservation of mass do go hand in hand. The second law of thermodynamics is our second bullet, and it states, when energy changes from one form to another, or matter moves freely, entropy in a closed system increases. Finally, we have our third law of thermodynamics that says, if an object reaches the absolute zero of temperature, which remember is 0 degrees Kelvin, its atoms will stop moving. Of these three, we have focused on numbers 1 and 3 this year, and therefore we're going to be focusing on this second law of thermodynamics in this lecture, which is going to help understand why chemical reactions happen the way that they do. It comes into play with this thing called Gibbs free energy. Now, free is in parentheses because sometimes you'll see it referred to as just Gibbs energy, or sometimes the Gibbs will come off and you'll see it referred to as free energy. It's up to you to know that all of these mean the same thing. All of them, no matter how you say it, will be symbolized delta G. Well, energy by itself is a measure of a system's ability to cause change. Thus far, when we've been talking about energy, we've been talking about it in terms of heat. So if we look at enthalpy alone, exothermic reactions are the ones that nature likes, and it's going to be referred to as spontaneous. Now, for you and me and your friends, spontaneous means like spur of the moment. All of a sudden, we decide to do something. But that's not what it means for chemical reactions. When a chemical reaction is spontaneous, it means it happens by itself, it being the chemical reaction. The chemical reaction happens by itself. Humans do not need to do anything in order for that reaction to occur. So, for example, the rusting of metal. The rusting of metal is spontaneous. We don't have to do anything. The metal will rust. Granted, it's a slow reaction. It's going to take a long time, but it is spontaneous. So when you look at enthalpy alone, just the heat, the exothermic reactions will be spontaneous. Remember, we've kept talking about all this year how nature likes things that are in low condition. And remember, I'm putting likes in parentheses because nature doesn't really have feelings. Things that are low energy is what nature prefers because it doesn't take a lot of work to get that state going. So exothermic, since the energy is given off, it's a low energy state, is what nature prefers. Conversely, endothermic reactions, the ones that absorb energy needs to go into the system, will be non-spontaneous. In other words, the chemical reaction will not happen by itself. So non-spontaneous. The chemical reaction will not happen by itself. Humans must interfere. So the burning of wood, the combustion reaction of wood, that is a non-spontaneous reaction. The only way that wood is going to combust is if humans interfere. We've got to supply some type of energy to help get that started. Another example, reacting baking soda and vinegar. When you do it, it just happens. That's an example of a spontaneous reaction. So when you now put this second condition of the big picture, what makes chemical reactions happen, when you put the thermodynamically favored aspect into it, not only do we need to look at enthalpy, which is part of this Gibbs energy, you also have to take into account the second law of thermodynamics, the entropy. So Gibbs energy looks at both enthalpy and entropy simultaneously. Gibbs energy is going to be calculated using this formula. Delta G is equal to delta H minus T delta S. Let's look at what all of these symbols mean. Delta G is Gibbs free energy. Delta H, as you know, is enthalpy. T, as you know, stands for temperature. S is new to us this lecture. S means entropy. And that's what we're going to be focusing on as part of this lesson. What is entropy? Before we get around to actually working through what these math problems will look like. But before we dive into entropy, let's just talk about how Gibbs free energy is going to tell us the same thing that enthalpy did when we looked at enthalpy by itself. When Gibbs free energy is negative, the reaction is spontaneous. Again, that means it will happen by itself. When delta G is positive, the reaction is non-spontaneous, meaning humans have to do something to get that reaction to work. All right, so like I said, we'll come back in a few minutes and work through some practice problems. But for now, let's focus a little more in depth on what entropy means. Entropy's symbol is this delta S, and again, it comes from the second law of thermodynamics. Scrolling back up to what we said, the second law of thermodynamics says when energy changes from one form to another or matter moves freely, entropy in a closed system increases. Matter moving freely. What we're trying to measure here is the amount of disorder in a system, or randomness. That's another word that people tend to use with entropy. Randomness. How does disorder or randomness link up to entropy? Well, a lot of disorder will have a high entropy. A lot of order has low entropy. Now, thinking about what nature likes things that don't take a lot of energy. So nature tends to like high entropy states because it takes less energy to be disorganized. Think of your rooms, right? You put in all this time and effort to get it neat and tidy and whatnot, and then as the days go by, it's so much easier to just take your dirty clothes and just leave them in a pile on the floor, and to take that wet towel when you get out of the shower and drop that on the floor too, and to leave your homework sprawled out all over the place and your books and whatnot. It is really easy to be disorganized or messy or random or have a lot of disorder. It takes energy to be neat or ordered. Oh my gosh, you have to bend down and pick up your clothes and actually put them in the laundry basket. Oh, it takes so much energy. Ha ha ha. So nature likes things that are in high entropy states or random or disorder because it takes less energy. When you're looking at the entropy in chemical reactions, because remember, we're trying not to talk about the energy aspect right now. Talking about entropy and enthalpy simultaneously is where Gibbs will come into play, but let's just focus on entropy. When you're dealing with them in chemical reactions, you're going to have to look at the state of matter. States of matter. Do that first. That's going to be your priority. And then, after all of your states of matter are the same, you're going to have to look at your overall number of moles. Here's what I mean. The states of matter that we've been working with have been solid, liquid, and gas. In terms of solids, they have a lot of order. The particles are tightly packed together. They usually have a definitive shape associated with them. Solids are going to be low entropy. As you move from solid to liquid, the particles start to separate and have a little bit of fluidity to them. And then as you progress to the gas, those particles are spaced so far out, they're random, they're moving around constantly. Here's where you're going to have your highest entropy. A lot of disorder. So if we're looking, for example, at a chemical reaction, let's say we're starting out with solid calcium and it's reacting with 2 moles of liquid water to produce solid calcium hydroxide and 1 mole of hydrogen gas. So if this is our chemical reaction and we're trying to analyze what's happening to the entropy, looking at my reactants, I'm starting out with a solid and a liquid. And looking at my products, I'm ending out with a solid and a gas. Well, you can kind of think of the solids as like canceling each other out. So I'm going from a liquid to a gas. Gases are definitely more disordered. So overall, my entropy, my delta S, will be increasing in this reaction. This reaction is getting more disordered. And looking at enthalpy alone, this is something that nature would prefer. This process would be spontaneous. All right. One other thing we have to add to this list of states of matter is when you're thinking of chemical reactions, there's that 4th unofficial state of matter, aqueous. Where do you suppose that would fall in? Well, you're right. It would definitely not be beyond solid, nor would it be beyond gas. It's going to be somewhere in the middle here. But the question is, does it go between solid and liquid, or does it go between liquid and gas? And the answer is, it goes between liquid and gas. The aqueous state has more disorder than just the liquid state because you're adding those solid particles, the solute. Maybe it's not solid, maybe it's liquid or gas. But because you've got these solvent particles that are trying to dissolve the solute particles in an aqueous state, that's going to lend itself to greater entropy or greater disorder than if it were just the liquid state alone. So in terms of ranking our states of matter, you have solid, liquid, aqueous, and gas going from the least amount of entropy to the most amount of entropy. Now you'll notice that we prioritized states of matter. The second thing would be your overall number of moles. If this chemical reaction were all the same states of matter, which they're not, which is why we didn't look at it, but if they were all the same states of matter, we would have a total of 3 number of moles of reactants and 2 moles of products. 3 moles to 2 moles, that's getting more ordered. So if the states of matter were all the same, and we then had to default to looking at the overall number of moles, the entropy would be decreasing. But that's not what we prioritize. We prioritize the states of matter. Let's look at one more. What if I had 4 moles of HBr gas reacting with 1 mole of oxygen gas to produce 2 moles of liquid water and 2 moles of liquid bromine? We want to know what's happening to the entropy. Priority, look at the states of matter. We've got gases converting into liquids. Gases are high entropy, liquids are lower. So the overall disorder is decreasing. Our entropy is decreasing because I'm getting more ordered. Excuse me. All right. If you'd like to pause the video now and watch the YouTube link that's provided for you in Google Classroom to try to additionally explain what entropy is and where you'll see it in your everyday life, you're welcome to do so. If you want to hold off and watch it until the end, that's fine too. All right, so let's get to our practice problems. Remember, what are we doing? We're trying to figure out why chemical reactions work. And we need to take into account both enthalpy and entropy simultaneously. And that brings us to Gibbs energy, or Gibbs free energy, or free energy. Again, you have to know all those things mean exactly the same thing. So we're supposed to calculate the change in Gibbs free energy for the following reaction at 25 degrees Celsius. Is the reaction spontaneous? The enthalpy for this reaction is negative 196.0 kilojoules, and the entropy is positive 0.1259 kilojoules per mole. Before we get into the math, let's just harp on this entropy for a second. The reaction has us going from the liquid state to the liquid and gaseous states. That's becoming more disordered, so it should make sense to you why that entropy value is positive. So it looks like that's something that's favorable. Looking at enthalpy, it's negative. Again, that's something that nature likes. It's exothermic. So it looks like this overall reaction will be spontaneous, but let's do the math to double check. So calculating Gibbs free energy, the formula is delta G is equal to delta H minus T delta S. Delta G is what we're solving for. Substituting in for delta H is negative 196.0 kilojoules. Then I'm going to subtract from that the T, which is temperature. Oh, whoopsie daisies. Uh-oh. This needs to be moles Kelvin. Sorry. Entropy's unit is kilojoules per mole Kelvin. Sorry. Our temperature needs to be in Kelvin. So 25 degrees Celsius plus 273 is equal to 298 Kelvin. So I'm going to subtract it from 298 Kelvin. And remember, this is the standard temperature for chemical reactions. And then our delta S is this 0.1259 kilojoules per mole Kelvin. All right. Negative 196.0 kilojoules minus, doing the math here, gives me 37.5 kilojoules. And then doing the overall math, negative 233.5182 is what the calculator gives me. Checking my sig figs, I'm going to need 4 of them. Nope, sorry, 3 of them. So it's going to equal negative 234 kilojoules, which is my delta G. And the question asked, is it spontaneous? Again, because it's a negative sign, yes, this is spontaneous. This reaction will just work. And for those of you who've never done it before, I don't suggest doing it right now, but yes, if you take your hydrogen peroxide and you pour it out into the sink and you're very quiet, you'll be able to hear the fizzing. You'll be able to hear the decomposition where the oxygen gas is coming out of the reaction, and then eventually all that you'll be left with is a puddle of water in your sink. Right? And we knew that it would be spontaneous because the enthalpy and the entropy were both favorable to what nature likes. Let's try one more. Again, calculate the change in Gibbs energy for the following reaction at 25 degrees Celsius. Is the reaction spontaneous? The enthalpy is 178.5 kilojoules and the entropy is 0.1591 kilojoules per mole Kelvin. Please change that unit. My apologies. Moles Kelvin. All right, let's just look at this. The enthalpy is a positive value. That's not spontaneous according to just looking at enthalpy by itself. Entropy, we're going from a solid to a liquid and a gas. It is increasing, which is why this value is positive, which is something that nature likes. So we've got a scenario where the enthalpy is not favorable, the entropy is favorable. Let's see which one's going to dominate when we look at both of them simultaneously. All right, so Gibbs free energy. Delta G is equal to delta H minus T delta S. Delta G is what we're solving for. The delta H is 178.5 kilojoules. I'm subtracting from that the temperature, which we said was 25 degrees Celsius plus 273, which is 298. So I'm going to subtract from that 298 Kelvin. And I'm timesing that by delta S, which is 0.1591 kilojoules per mole times Kelvin. All right. So 178.5 minus, when you take 298 and multiply it by decimal point 1591, we get 47.4. 47.4. And now, doing our final subtraction, 178.5 minus 47.4, we get 131.1 kilojoules for our delta G. Is this spontaneous? Well, because it's positive, nope. It is a non-spontaneous reaction. So getting back to that question about favorability, right? We had enthalpy, which was not favorable, enthalpy that was, and you're like, well, which is going to dominate? If you didn't notice it as we were doing the math, it really all depends upon the temperature, right? If that T delta S value was able to dominate, in other words, if this 47.4 was larger than the 178.5, then our answer would have been negative, and it would have been a spontaneous answer. Spontaneous reaction, please excuse me. So you have, in terms of which is more favorable, it all depends upon the temperature and whether that T delta S will dominate compared to the non-favorable enthalpy. So to end things off, some of you may find this helpful, others may not, and that's okay. Wherever you're at, you're at. If let's take them one at a time. If your delta H is negative, which is what nature likes, and your delta S is positive, which is what nature likes, your delta G is always going to be negative, and you're always going to be spontaneous. Conversely, if your enthalpy is always not favored, and your entropy is always not favored, your Gibbs free energy will always be non-spontaneous. But these last two here deal with, well, what's going to happen if you have an example of something that's favored and then not favored, right? Not favored and favored. How are you going to know? Well, again, it depends upon your temperature, whether or not that T delta S factor is going to dominate, right? So if your T delta S is going to be great enough to overcome, right? That's what we mean by the high temperature. If it's great enough to overcome the value of your favored enthalpy, then you'll be non-spontaneous. But if you're at a low enough temperature, where T delta S will be smaller than the negative number, then you'll be spontaneous. That negative number will still dominate. It's all algebra. But again, like I said, some of you may find this helpful, others may not. It all has to do with the domination of the T delta S product. So I do hope that you found this helpful. Again, some of you may not, and that's okay. But at this point in time, if you haven't already watched the YouTube video, please go ahead and do that. And then give it a chance to try to solve the problems for Gibbs free energy homework. All right, let me know if you have any